Okay, I'm recording this in advance so you all get to see it on Thursday because we won't have class. So today I want to talk about related rates. If you remember when we were talking about chain rule, we talked about an expanding circular ripple in a pond. I want to take this idea and generalize it. Let's consider a balloon. And I'm, for the moment, going to assume this balloon is a sphere. Now, as I put air into this balloon, I know that two things will change at the same time. Both the volume and the radius change together. And it's this together that matters. Because as I think of the air going in, I don't want to think about how fast the volume changes per centimeter of increase. I want to think of how fast the volume changes over time. So let's think about this. Can I relate the change in volume to the change in the radius? Again, and I asked this question the other day, if I think about a spherical balloon increasing in both volume and radius, it might benefit me to know how the radius is changing, so I know whether or not the balloon slams into my nose and or breaks my nose when it hits me in the face. So let's think about this. The first thing I need to be able to do this is a little bit more information. I need to know how fast my volume is changing. So let's make an assumption. We're going to go in 100 cubic centimeters per second. So every 10 seconds, I add a liter of air to this particular balloon. How fast is the radius changing? Well, let's actually ask the question the way I was reading it. How fast is the radius changing when the diameter is 50 centimeters? So I have to know either a particular moment in time or a particular moment about the balloon. So I know right at the time I'm looking at, diameter is 50 centimeters. Okay. First thing I should do is make a picture, but I already drew my little balloon up here. I'm going to add to this picture. I'm going to add the radius. So I can picture what's going on. As the balloon's volume increases, the radius gets larger. Okay. Now that I know what I'm trying to relate, volume and radius, I need to know, is there an equation that relates them? Is there any equation that relates the volume of a sphere to its radius? If you don't already know the formula for the volume of a sphere, you should, but you can look it up in the back of the textbook. I know that the volume is 4/3 pi r cubed. Now, what information in here do I already know? Right at the moment I'm looking at, I know how fast air is going in, and I know a diameter. Wait, this is a rate. It's not just any rate, it's a rate of change. This 100 cubic centimeters per second, that is a change in volume with respect to time. And this diameter, oh, wait a minute, diameter is not mentioned down here at all. Oh, right, all right, wait a minute. Diameter is twice radius. So if I know that the diameter is 50 centimeters, then I know that the radius is 25 centimeters at that point in time. But what I want to find is how fast the radius is changing. What's that? Ah, that's a rate. It's a rate of change. That's a derivative. And it's not just any derivative, it's dr dt. Okay, here's where the fun part starts to go. I say to myself, none of these are about t. None of them have t's. Back to implicit derivatives. The y was assumed to have x's hiding in it. I am going to assume that the two variables I have are really functions of time. And then what I'm going to do is I'm going to say, oh, well, let's take this equation and let's take the derivative with respect to time everywhere. Oh, wait a minute. Derivative of v with respect to time. Well, that's v prime of t. Or if you'd rather, dv dt. And over here, 4/3 and pi, those are just numbers. Constants being multiplied, stay out front. What's the root of r cubed? There should be a chorus. I'm not here to hear it. 3r squared. But wait, there's more. What more? The what more is dr dt, or r prime. I don't care which way you write it. I prefer the dr dt, but that's me. Hey, wait a second. I can take the information I know and I can put it in here. And if I do that, I can solve for the thing I'm trying to find, which is right here. Before I do that, I notice this 3 and this 3, they cancel. So really, dv dt was 4 pi r squared dr dt. And now I can put in all the information I know. dv dt is 100. R is 25. And if I solve for dr dt, I get 100 over 4 times pi times 25 squared. Take out your calculators, give me a decimal. Or you could simplify this as a fraction, because 4 times 25 is 100. But I think a decimal would be a little more useful here. This is approximately 0.013. What are the units on this? I know. Instead of just figuring out the units randomly, let's go back over here and do the unit in here. This is centimeters cubed per second. This is unitless, but this is centimeters squared. So here I have cubic centimeters per second, but I'm dividing by centimeters squared, and that makes this centimeters per second, which makes sense because that is a change in length. The radius is increasing at a little over a millimeter a second. .013 centimeters per second, or 0.1 millimeters. Sorry, not 1. Oh, okay. The thing that is critical here, the single piece that is the most important, is to ensure that our expressions relate to changes. Okay, on page 249. Page 249, we have a box. The box tells me what to do. The box says, read carefully. I'm going to insert another word into this. Read the problem carefully twice. The first time you're just reading it. Just go through the whole thing. Second time, you think about what you're asked to do. Draw a diagram. We draw a little picture of a balloon. We introduced our notation. Assign all quantities that are functions of time symbols. We had V, we had R, we assigned them symbols because those were the things that were changing. Express information and the rates we want to know in derivatives. And then relate them. Now it says here, if necessary, use the geometry of the situation to eliminate one of the variables by substitution. There's an example, but I'll do another one. Use the chain rule, differentiate with respect to t. Again, implicit derivatives, logarithmic derivatives, all of this depended on my ability to do the chain rule. The chain rule is the most important thing here. Plug in the information and get what we know. Okay. Let's pull a problem from the text. Here you go. Problem number 22. A boat is pulled into a dock by a rope attached to the bow of the boat, passing through a pulley on the dock that is 1 meter higher than the bow of the boat. If the rope is pulled in at a rate of 1 meter per second, how fast is the boat approaching the dock when it is 8 meters from the dock? What? Oh, okay, wait a minute. See, there's a little crank on my pulley here. If I turn the crank to bring the rope in, how fast is the boat going that way? That's all I want to know. Page 252, there's my picture. But because I don't want to rely just on their picture, I'm going to make one of my own. I have a boat in the water. It is going this way. I have a dock. I have a rope. A pulley. Pull in the rope at, what did it say? Oh, yes, 1 meter per second. Plus, I know that the pulley is 1 meter above the bow of the boat. Notice not above the surface of the water, but above the bow of the boat. I also know that the distance from the boat to the dock is 8 meters when I want to know about how fast the boat is going that way. Okay. There's a little right triangle here. I'm going to put it over here for the moment. The boat's in this corner. The pulley's in this corner. What do I know that's changing? Oh, I know the rope is changing. So we give it a letter because that's changing with respect to time. I also know that the distance from the boat to the dock is changing. I don't want to use D for distance. I'm going to use L for length. Because otherwise it's DD, and that just bothers me. So I'm not going to use D. Okay. I want to know the relationship between these two sides. Oh, and I forgot. I know the length of this side. This is 1. Now, it's safe to assume that the pulley isn't getting any higher or lower. We haven't taken into account whether the tide's coming in or whether the waves are bothering it. We're just looking smooth as glass water. what can I use to relate these three pieces? Well, as the boat comes in, the angle of the rope is going to change, so I don't want to use the angle. That'd be another thing changing in time. But all of these lengths are going to change. Well, these two are going to change. That's not going to change. I can use Pythagoras. I know that L squared plus 1 squared is R squared. 1 squared is just 1. Here's my equation. That's the critical piece of information. Okay. I need you all to make a decision. I have some information here. This number 8, what does it relate to? Oh, it relates to L. What are we trying to find? We're trying to find how fast the boat is moving in. Well, that's the rate of change of this distance. That's the rate of change of L. And this one, that doesn't change at all. What about this one? What's this one? That's the length, the rope changing, right? That's dr dt. Wait a second. I have a little sign convention here. Is the rope getting longer or shorter? The rope is getting is shorter, so the amount of rope is getting smaller. I think the change in the rope should be negative. If you don't use a negative number here, you're just going to get a positive answer where I get a negative one. That's okay. With me so far? I was hoping at this point I would see nodding, but I'm alone in my office and you're not here. So I'll nod. Okay. If this is the equation that relates my quantities, I need to take the derivative with respect to time. I am assuming that L has t's in it and that R has t's in it, because that's what it means to be a function that changes with respect to time. So I take the derivative with respect to t on both sides. Chain rule, chain rule, chain rule. Derivative of L squared is 2L dl dt. Derivative of 1. There should be a chorus here. 0. The derivative of R squared, 2R dr dt. So now I know that in order to find dl dt, I need to divide. And dl dt is R over L, because the 2's cancel, dr dt. And I can plug in everything I know. I know L, I know dr dt, I don't know R. All right, wait a minute. How can I get R? Oh, I can go right back up here to where it says star. And I can put in the L I know, and I can get out the R I know. When L equals 8, 8 squared plus 1 is R squared. 8 squared is 64, plus 1 is 65. And that means that R is the square root of 65. Now I have all the things on this side. Square root of 65 over 8 times negative 1. And again, I'm going to ask, do the units here make sense? Let me go back over here. L is in meters. R dr dt should be meters per second. That's what it says right here in my picture. Meters per second. And R should be in meters. So over here I have meters over meters times meters per second. These cancel, and I get dl dt is in meters per second. Now again, if you give me a decimal here, you get negative 1.00778 meters per second, which means my length L, because this is negative, is getting smaller, just like R was getting smaller. If you had chosen this dr dt to be positive 1, then this would be positive as well. And I'm okay with that. You could fix that in the words, because you could say, oh, the length is decreasing at 1.00778 meters per second, decreasing at a positive rate. Questions? At this point, if you have questions, you should be emailing me. Let's try another one. The classic example of this idea, most commonly used example, is a ladder leaning up against the wall. And we make the assumption that this 10-foot ladder is sliding down the wall. It's falling out from under me. Oh, crap. If I'm up here, I'm going to hurt myself. How fast am I falling? Well, I need to know some more things. How fast is the ladder sliding down the wall when I know it's moving away from the wall at 4 feet per second? Remember, the ladder is 10 feet long. And let's say that the bottom is already further away. Is the bottom further away? No, the bottom of the ladder, yes, the bottom of the ladder is 6 feet away from the wall. There. Now I've written down all the information that was given to me in this problem. Page 248, if you want to see the textbook's picture. Okay, two things are changing. The horizontal distance from the wall and the vertical distance from the wall. So let's label these. I don't care what you label them. You can label them X and Y. I'm going to label them horizontal and vertical. Because to me, that makes sense. But again, that's my interpretation. You can label them however you want. Okay. This 4 feet per second, what does it represent? Feet per second, that's a rate of change, so that's a derivative. Which thing is changing at 4 feet per second? The horizontal. So that's dH dt, and that's my 4. And that's getting bigger. I'm going to leave it as positive. What's this 6? The bottom of the ladder is 6 feet away from the wall. That's H. The only other number I know right at the moment is that the ladder is 10 feet. So I have this picture. Oop. Doesn't help if I label it backwards. What were we asked to find? We were asked to find how fast the top of the ladder is falling. When the bottom of the ladder is 6 feet away from the wall and it's moving at 4 feet per second. That's about this side. But that's how fast Is it falling? That's how fast it's changing. That's what I want to find. What relationship can I use here? Oh, I can use my Pythagorean theorem again. But this time, it's the hypotenuse that's not changing. So when I think about setting this problem up, I start by saying, there's Pythagoras. And these are the things that are changing in time. So this is the equation I want to take derivative of. With respect to time, derivative of h squared is 2h. But wait, there's more. dh dt. Because I'm taking my derivative in t, not in h, not in v. Same thing here. Derivative of v squared is 2v dv dt. What's the derivative of 10 squared? Well, wait a minute, 10 squared is 100. What's the derivative of 100? That's a constant. Its derivative is 0. My goal is to find dv dt. Let's get it all alone. 2v dv dt equals negative 2h dh dt. Cancel the 2's, and I get dv dt is minus h over v dh dt. And according to what I have written here on the left, h is 6, dh dt is 4. What's v? I don't know. Oh, but I can figure that out. I take that v, I take the h we know, I put it in to find v. 6 squared plus v squared equals 10 squared. 36 plus v squared equals 100. So v squared is 64. That makes v equal to 8. So now I can get dv dt because I have all the numbers I need. dv dt is minus h over v times dh dt, which gives me it's negative 6 over 2, negative 3. What are the units on that? Well, it's a change in length, and length at the moment was measured in feet, so that should be feet per second. Let's check. H is in feet, V is in feet, dh dt is in feet per second, so I have feet on top, I have feet per second here, I have feet on the bottom. Those cancel, I get feet per second for a unit. I find unit analysis to be absolutely critical to making sure I've actually solved for the piece I want to solve for. Questions? Again, since I'm not physically there, you should be emailing me. Now, you may think that every time you see a triangle problem, you're going to use Pythagoras. And that's unfortunately not true. Depending on which problem we're doing and what we're looking at, sometimes we use Pythagoras, sometimes we use other stuff. Here, for example, in example 4, we have a car heading west and a car heading north. But what we're actually looking for is the change in the distance between the cars, and this is going to use Pythagoras. Yay, another triangle, another use of Pythagoras. A man walks along a straight path with a speed of 4 feet per second. A spotlight located on the ground 20 feet from the wall is kept focused on the person. At what rate is the spotlight rotating? This is not about changing distances. This is about angles. When the man is 15 feet from the point on the path closest to the light, so here's the point closest to the light, that makes a right angle from the light. The man is 15 feet away, that's our x value. He is walking at 4 feet per second. That's change in x with respect to time. I want to know about change in theta. What relates x and 20 and theta? The tangent. I need trig instead. Depending on the problem, we may have lots of things we need. Let me give you example 3 out of the text, page 249. We have a tank. But the tank is shaped like a cone. Now, why would you shape a tank like a cone? Because you're using it as a filter. Now, this is a fairly large tank. The radius of the base is 2 meters. The height of the tank is 4 meters. Water is being poured into the tank at 2 cubic meters per minute. By the way, a cubic meter is a lot of water. This is 2,000 liters a minute, 500 gallons roughly a minute. It's a lot of water. Find change in height when the height is 3. Oh boy. All right, wait a minute. I've got water in the tank. The tank is 4 meters deep, but the water itself is at a height of 3. That's why I've labeled it H prime. I shouldn't use prime. Prime means derivative. Let's call it HW. That's the height of the water. This is the height of the whole tank. This is just the height of the water. Okay. Huh. I need to know the volume of a cone. Now, again, this may or may not be something you automatically know, but you can look in the geometry part in the back of the book, and I know that the volume of a cone is 1/3 the size of the base. The base is a circle with a given radius times the height. Please notice my problem. Water is going into the tank. This number right here. What is that the change in? That's the change in the volume. So that's dV dt. Cubic meters per minute, volume per time. In order to do this, I need to know R and H. But I only know H. How do I get R? Right here, this is the radius of the water. I don't know what it is. I really can't have two different things change on this side at the same time. If I want to take derivatives with respect to time here, I have two different variables and I don't know how to do that. And I only have one piece of information about height. I don't know the radius. Okay, wait a second. Let's look at what I do know right here. I have the tank itself. The tank itself has a height of 4 and a radius of 2. The water has a height of 3 and a radius of unknown. But if I think about the blue triangle versus the purple triangle, I know that those triangles have a lovely geometry problem. Well, geometry property, not problem, a property. They share this angle right here. That's the same angle in both of these triangles. It's the same angle in the blue triangle as it is in the purple triangle. And if the two angles, sorry, if the two triangles share one angle, they also happen to share another angle. The height is perpendicular to the radius. This is a right triangle. And if they share this angle and this angle, then this angle must also be the same. My three triangles have all the same angles. That means they're the same shape. These are similar triangles. And that means that the ratio between these things is the same in each triangle. So I can use this idea to change between R and H. Which one do you want on top? Oh, H, I hear somebody mutter in my own head. So I would say that H over R is equal to HW over RW. Height versus radius, height versus radius. But I know these numbers. That means that I know what's going on here, that HW is 2RW. Or if you'd rather, RW is a half HW. I don't care which one you put it in until I go back and I look at what I'm actually after. I want information about H. So I don't want R's, I want H's. I want to use this equation that we just came up with to turn this into something that's only about H. So I'm going to rewrite my volume equation with no R's in it. And with no R's, means I got to get rid of the R right here. So now my volume equation becomes R squared H. But instead of R, I'm going to write 1/2 H. Please notice I got to square that. So that's 1/3 pi, square a half, you get a 1/4 H squared, but then another H gives me an H cubed, which is the same as 1/12 pi H cubed. So this is what the book meant by, if necessary, use the situation to eliminate one of the variables. I can't have calculus with 3 variables in it yet, not until we get to Calc 3. We're not there now. But now I have something about H and V, and since I want dH dt, and I know dV dt, I can take my derivatives in time. dV dt is 1/12 times pi times the derivative of H cubed, 3H squared, but wait, there's more, dH dt. And now I put all the numbers in I know. dV dt is 2, and H was 3. So I get to solve for dH dt now. 2 times 12 divided by 3 times 3 times 3 is 27 pi equals dH dt. 36/27, right? No, 24/27. Those are both divisible by 3. That's 8/9 pi. Out comes my calculator. And 8/9 pi is, don't forget the parentheses around the bottom. Please notice what happens when I do it without the parentheses. It does 8/9 and then multiplies by pi. I need to divide by pi. I need it all in the denominator. This is the correct answer. This is not. So that's the HDT. Let me write that number down. 0.283. What are the units on that? Well, that's change in height. Height was measured in meters. Time was measured in minutes. This should be meters per minute. Let's go back and check. 2 was in cubic meters per minute. This was in meters squared. So this is in meters squared down here. Yep, when I cancel that, I get meters per minute total. Perfect. 28 centimeters per minute. Little over 11 inches a minute. It's rising pretty quickly. But as we get higher up the tank, the water rises slower because the tank is wider at the top. If your tank narrows at the top, if your cone was the other way around, well, then we'd have a different result, wouldn't we? Questions? Sometimes the problem we choose tells us more than we think it does. Problem number 32. A kite 100 feet above the ground moves horizontally at a speed of 8 feet per second. At what rate is the angle between the string and the horizontal decreasing when 200 feet of string has been let out? I'm not Charlie Brown who's going to get his kite eaten by the tree, but let's think about this. A kite is 100 feet up. It is moving horizontally at a speed of 8 feet per second. At what rate is the angle between the string and the horizontal decreasing when 200 feet of string has been let out? I need to draw a picture to understand what is going on better. A kite. A kite. 100 feet above the ground. Is moving horizontally at a speed of 8 feet per second. Flip a coin. I decided the kite is going to be moving to the right. At what rate is the angle between the string and the horizontal decreasing when 200 feet of string has been let out? That means there's a person on the ground holding the string. Is the person over here or over here? If they are to the right and the kite is moving this way, then the angle will be getting bigger. So the fact that they told me that the angle is decreasing tells me that the person is on this side. And the angle here is what I want to know about. How fast is the angle between the string and the horizontal? I might as well just put that at the person's height. but then I would have to say that the stop is here. To hell with it. There's my angle. Ignore this garbage. How fast is the angle between the string and the horizontal decreasing when 200 feet of string has been let out? I have a triangle. Again, I am assuming that the ground and the string are the ground and the kite are at right angles to each other. So I know this is 100. I don't know that. I know this is 200. This is the angle we are concerned about. But I know the kite is moving this way. That means this is changing. That means this needs a letter. I need to know what to call this. Normally I would say it's a distance. I don't like using D, so we'll call it H for horizontal. And this 8, that 8 represents what? That 8 represents the change in horizontal. It says we are moving horizontally, so I know dH dt is 8 feet per second. It's positive because we're going that way, and that's where the direction we're measuring H. So H is getting bigger. I'm going to use my change to be positive. This was problem 32. Okay. With me so far? If I want the height to stay 100, then the amount of string needs to be changing too. Otherwise, if the string was fixed, height would be going down. I wouldn't be traveling horizontally. So my amount of string is also changing. That's why that gets a letter. Because we said we want to travel horizontally, I need to keep the string growing. Huh. How can I relate H to the rest of this? If I use Pythagoras, it doesn't tell me squat about the angle. So Pythagoras is unfortunately the wrong way to go here. Crud. Pythagoras is the wrong way to go. I need something else. Well, I could use trig, right? We have 6 different trig functions. Let's try cosine, right? Because this is a horizontal angle. It's the adjacent side. Let's try the cosine. What do you know about cosine of theta? Well, cosine is adjacent over hypotenuse. That's h over s. Oh, wait a minute. If I go to take the derivative here, I've got too many variables. And s is changing because this is going horizontally. I can't use that one. Same reason I can't use sine. Sine theta would be opposite over hypotenuse. And again, s has to be changing, otherwise my kite wouldn't be moving horizontally. Wait a minute. Tangent theta. Tangent theta is opposite over adjacent. That works because that only involves h, and h is the thing I know the change of. Wonderful. Here's the equation I want to use. Okay. I want to take the derivative here because I want to know how the angle is changing. I want d theta dt. And I have dh dt, so this is the equation I use. What's the derivative of tangent theta? Everybody chime in wherever you are. Secant squared theta. But wait, there's more. Because I was doing the derivative of tangent theta, I'm doing my derivative in t, I get d theta dt. Now what about here? I'm going to cheat. 100 over h is 100h to the negative 1. Power rule instead of quotient rule. I am a lazy SOB. I want to do as little, as simple a derivative as possible. Change quotient to product, or in this case, just to power rule, and my life gets a lot easier. Great. I know dh dt. I don't know h. I don't know theta. Well, I actually don't need theta. What I need is secant theta. Because if I know secant theta, I can then square it. Let me go back to my picture up here for a second. This is when I look, right? So let's take a look at that. Well, now I can use Pythagoras. I know that h squared plus 100 squared equals s squared, but we are told we are doing this when 200 feet of string has been pushed out, which means I know that h squared is plus 100 squared is 200 squared. Oh, wait a minute, that's h squared plus 10 to the fourth. It's 40,000. Means that h squared is 300,000, which is 3 times 10,000. But the square root of 10,000 is 100. So h is the square root of 3 times 100. Now, you might be saying, how does this help me with theta? Well, now I know all three sides of my triangle, and this is theta. If this is theta, secant is hypotenuse over adjacent, because secant is 1 over cosine. There you go, hypotenuse over opposite. So secant theta, I can just use these numbers. Great. I can now plug all the information I need into here. Secant squared theta. Secant theta is hypotenuse over opposite. That's 200 over 100 square root 3 squared. D theta dt equals negative 100 h to the negative 2. I put a negative power, goes in the bottom. H squared. Wait, I have h squared right here. 300,000 times dh dt. But we know dh dt. dh dt is 8. Ta-da! I have all the numbers I need. 200 over 100 is just 2. That gets squared. 2 zeros cancel there. I get negative 8 over 300. Square this. Square 2, you get 4. Square the square root, you get 3. Multiply by the reciprocal. d theta dt is negative 8 over 300 times 3 over 4. That's negative 2 over 100, or negative 0.02. What are the units on this? Oh, I'm measuring a change in angle, right? So this is radians per what? Per minute, per hour? Oh, go back up to the original part of the problem. Per second. Now, if I go back here, I can actually fit all of those numbers in here. This is length, right? This is feet over feet. Those are going to cancel out. H squared is feet squared. The h dt is feet per second, isn't it? What was the 100? That was in feet. So I have feet squared, canceling with feet. I just get per second. And that makes sense because radians are technically without a unit. This is per second. This is the right unit. Wow. Does it make sense that my angle is a negative change? Yes, because it's getting smaller as we let out more string and the kite travels further away from us. Makes perfect sense. Wow, matches up with my picture of me holding the kite string and letting the string out. I don't care what problem we are working with, no matter what problem we are working with. This same idea is going to carry through. I need another piece of information. Okay, let's pick another problem at random. We'll find one. How about problem 40? All you chemists. When air expands adiabatically without gaining or losing heat, so all you eventual thermo people, all of you pressure cycle, same idea. Pressure and volume are related by PV to the 1.4 is a constant. Suppose that at a particular instant, the volume is 400 cubic centimeters and the pressure is 80 kilopascals and decreasing at a rate of 10 kilopascals per minute. At what rate is the volume increasing in this instant? Now, I have not done this problem. I just pulled it out of the book, and I'm going to go through it from scratch with you all, right here, right now. Ready? Problem number 4. When air expands adiabatically, its pressure and volume are related by the equation PV to the 1.4 equals C, a constant. Now, I am going to tell you one thing, and that's that I need unit consistency. Suppose the volume at a certain instant is 400 cubic centimeters and pressure is 80 kilopascals. Well, kilopascals has a lower case a, kPa, and is decreasing at a rate of 10 kilopascals per minute. 10 kilopascals per minute, wait a minute, that's change in pressure over time. That's dP dt. Find the volume change. Find how fast volume is increasing. Oh, that means I need to go back and change something. The change in pressure is decreasing. That should be a negative number. I promise we'll go through why that should be positive or negative in a minute. Oh, in a section or two. But I want volume versus pressure. That's not what this equation is. So let's rewrite it. I'm going to write volume to the 1.4 equals C p to the negative 1. C is a constant. So that's okay. As a matter of fact, we could figure out what that constant is because we know those two numbers. 400 cubic centimeters is C times 80 kilopascals to the negative 1. Now, I am mixing my units here. I'm using pascals, which is newtons per square meter, and I'm using cubic centimeters. So I have to remember my units choice matters. All of my volume work is going to be in cubic centimeters. I'm okay with that. So what this means is that C is 80 times 400 to the 1.4. I'm not even going to bother to simplify it. I'm just going to leave it like that for the moment. I promise I'll use the number in my calculator later. But I don't need the number right now. Okay. Let's do this here. Both of these are changing in time. I have dp dt and I want dv dt. So I take the derivative. 1.4 v to the 0.4 dv dt. C is a constant, it says, minus p to the minus 2. dp dt, chain rule again. Now my goal is to find this, so I'm going to eventually move everything else over there. But let's put in the numbers we know. 1.4 v. V is 400 to the 0.4. dv dt equals minus c, 80 times 400 to the 1.4, p to the negative 2. P is 80. dp dt, negative 10. Everything on the right-hand side is a number. So dv dt, this is to a negative power. It should go on the bottom. Ew. Hey, wait a minute. I have an 80 on top and an 80 on the bottom. That'll simplify. I have a 400 to a number and a 400 to a number on the bottom. Let's do the algebra before. Minus a minus becomes plus. 80, 400 to the 1.4 times 10 over 80 squared, 1.4, 400 to the 0.4. Well, this 80 will cancel with one of those. The 400 here and the 400 will just leave me 400 to the 1 on top. 400 times 10 over 80 times 1.4. 400 over 8. Wait a minute, that's 50. So the answer is 50 divided by 1.4. $35.7 what? This is change in volume. Volume was in cubic centimeters. Time was in minutes. This is centimeters cubed per minute. And the volume is getting bigger because the pressure is getting smaller, and pressure is inversely proportional to volume. Well, volume is the 1.4. There you go, people. By the way, if you had chosen to make your volume 0.4 liters, you could convert 4 liters. You could convert from cubic centimeters to cubic meters, right? Then kilopascals, your meters would be in the right units. I didn't need to do that. I could leave this in that esoteric, bizarre unit, and it would work. Please notice problem 37 uses Boyle's law. Same idea. Pressure times volume is a constant. Here they're holding the temperature. Because remember, we have pressure and volume and temperature are all related by the ideal gas laws. So in this version, adiabatic behavior, I've decided that I will work with no temperature change. In Boyle's law, again, there's no temperature change. In Charles' law, I believe we actually have temperature change, but no volume change, so it's pressure that's changing. I think chemistry was a long time ago, people. But the ideal gas laws work together and tell me that pressure times volume is equal to number of moles times some gas, ideal gas constant times the temperature. So PV over T is constant, based on the number of moles of gas you are working with. There you go. Now, in case you think this is esoteric and slightly psychotic, I don't use this particular calculation because I don't do chemistry. But if we're talking about non-heat pressure volume constraints, we could look at heat exchangers. Well, they actually exploit the fact that temperature is involved in this equation. If you think my idea of the angle of the searchlight is a crazy problem, take a look at number 45. A TV camera is positioned 4,000 feet from the base of a rocket launch pad. The angle of elevation of the camera has to change to keep the rocket in sight. The mechanism for focusing the camera has to take into account the increasing distance. So I need to know how fast is the angle turning and how fast is the distance increasing. So I have to do both of those calculations with the change in angle and with the change in distance to keep my rocket in focus and in sight. If you are not familiar with the Space Shuttle Challenger explosion, the camera wasn't tracking properly. And the camera was not focused on the shuttle when it exploded. The camera missed. The close-up camera following the shuttle missed the explosion. The ground camera caught it. By the way, at this time in Houston, the launch is in Florida. The shuttle is in Florida, heading up and going east. Houston, Texas, where the command center can't see the shuttle. All they see is the telemetry, and then the telemetry goes blank. And they just knew there was a problem. The shuttle stopped responding. It sounds stupid, but these are exactly the ideas, and change in temperature, pressure, and volume are exactly the ideas we want to keep track of when we are doing this sort of information. By the way, you can now go back and look at the ripple in the pond question a different way. We can think about the fact that the pond ripple, we knew the radius was expanding at 60 centimeters per second. And we know the area is pi r squared. So if I want dA dt, that's pi times 2r times dr dt. And I don't actually need to figure out everything in terms of t, except I don't have the radius, do I? Oh, but I do know that it's 60 centimeters per second, so r is 60 times t. Slot that right in here. You get exactly the same result you got on the homework you turned in yesterday, and I would have given back to you today, but I'm instead going to get back to you tomorrow. Same process, different perspective. All right, ladies and gentlemen, unless I'm grossly mistaken, tomorrow, Friday, is another question and answer day. It'll be on 3-7, 3-8, and 3-9. I hope to see you all then. Thank you for paying attention. Have a wonderful rest of your day.